Hello everyone, welcome to the molecular spectroscopy of physical chemist perspective week 10 live session. Here I am Prabhu Chaudhary. I am a PMR from IIT Bombay today, where we discuss some live queries or some assignment problems or the whatever taught in the NPTEL lecture series. We discuss that here. So today actually we are going to discuss about we are not going to discuss about the usual problem solving what we are doing for the past few weeks, a couple of weeks. And so today what we are going to do is we are going to only discuss about the week 11 lecture what sir has been taught. Firstly, the thing is that the titles that is given in the Soyam portal, I think wherever you are learning from, if you are learning from the YouTube, directly from the YouTube, then there was no such problem. But in Soyam portal, the title of those videos might be confusing because whatever the title says, the subject matter is not the same because that has been interchanged with that of the week 12. So please you can follow the YouTube video also, so that you understand that the thing is the some difference is there. Means you can go by the only by the whatever there is the video, don't go by the title. That's all. And so what we are going to discuss today is let me write one by one. So today basically we are going to discuss week 11 topics. Week 11, all the lectures from 55 to 59. So in 55, lecture number 55, where Sir has discussed briefly regarding that, um, briefly regarding the um, basics of NMR spectroscopy, nuclear magnetic resonance spectroscopy. Here, till now we are discussing about the electronic states, rotational spectra, hypertonic spectra. Now we are coming back to the nucleus, where we are going to talk about the NMR spectroscopy. Now there we have there Sir has talk about how that interaction, what is the interaction energy, what are the nuclei which will have some nuclear spin, what will be the energy difference between the two different spin. Then in lecture 56, how does the coupling happen? Coupling happen between two, two distal protons, and in 56, 57, and then 58 and 59, Sir has discussed how the uh, coupling happens between similar proton from equivalent protons, or the protons coming from the same attached to same carbon, something like that. So we'll start from that lecture 55 itself. So I'll first check if my so I am recording this session and you can find this video in YouTube. So I'll just check if the my audio I am audible or not, my audio is there or not. Okay, so for that I'll just uh, pause this maybe. I'll like to pause. Is there any option of pausing? I guess there is no such option, I guess. Okay, so I hope I'm yeah, the audio I can understand. I think it's okay. So let us go back and let us start. So the first thing is that so let me go to the presentation mode. Now here we will discuss that the first week lecture 55, basics of NMR spectroscopy. So you can understand, right, that for which atoms we are going to see this, which will be NMR active nucleus. To be NMR active, like NMR active, like in case of IR active or IR inactive or Raman active, something like that, or if we can see rotational active, rotational spectra will be there or not, or what. There was some thing related to the dipole moment, right? For rotationally, if rotational spectroscopy active molecules will have some permanent dipole moment, right? And in case of IR spectroscopy, you have seen that to be IR active, there should be some change in the dipole moment during the oscillation or the vibration. And for NMR active, actually those atoms will be NMR active where their nucleus spin is actually non-zero. So in case of even atomic mass and even atomic number like 16 or um, this kind of atoms will have zero uh, zeros nucleus spin. Now, in case of even atomic mass is nothing but the sum of the total number of proton plus neutrons. Atomic mass and uh, odd atomic number. So there are few atoms like 14N, right? Or um, maybe 10 boron, right? These kind of, or maybe deuterium, these have uh, whole numbers, or you can say uh, whole integers, you can say, as nucleus spin, that is I, right? Integer. So, and in case of odd atomic mass like 13C proton, then normal 1H, those have half integer value of nucleus spin. Okay, so they these are NMR active and this is not NMR inactive and NMR active. Now, so when there is, so this NMR spectroscopy we need an external magnetic field. So this uh, nucleus spin is actually, so what can be the nucleus spin? One alpha, one beta, right? So not for this. Suppose your nucleus is going to be interacting with an external field. Wait, I think there is some problem with Google Meet. Let me handle that. Stay in the call. Okay. Then come back. So there should be some interaction energy between. So what is happening? You have some nucleus spin. Okay. Think about proton. Okay, 1H. So let us think about 1H. So what is the spin? Spin is half S, right? This is nucleus spin, right? Nucleus spin, not the electronic spin. Okay, nucleus spin is half. So what are the values of MS? MS could be plus half and minus half. So actually spin is always half, but MS, that quantum number, that is plus half and minus half. So if someone asks you that what is the nucleus spin of proton, then it is half, not minus half or plus half. So the plus half we generally denote by alpha and minus half is beta. Suppose there is no external electronic field, then the energy of these two states related to these two spins are actually equal. So alpha beta will be staying at a same position. Okay. Now when there will be some external field, so there is alpha beta, both are in same. Okay, alpha beta. There is no external field, external magnetic field. Now when there will be some external magnetic field, it will actually get separated into some two states. One will get stabilized, another will get destabilized. I will come back to very soon I'll come back to the whatever the energies will be there. So it will actually tend to be so it will going to be non-degenerate. First it was degenerate, now it is in presence of in presence of magnetic field, external magnetic field, that is B0 suppose. Okay, now so so in this purpose let me first know whatever is the interaction energy is going to be. E is actually minus mu into B0. Mu is the dipole moment and B0 is the external magnetic field. Now this mu is actually gamma into I. So this gamma is known as gyromagnetic ratio, which is different for ferromagnetic ratio. It is different for different nuclei. So for proton, so the gyromagnetic ratio, I think for proton is actually is actually 4 times of gyromagnetic ratio of carbon. So this is what actually makes different. I is the it's not the spin. It is the um, momentum. Am I speaking it correctly? Yes. Now, now this gamma I is actually and we can also have some relationship for numerical problem. This is going to be important, which is gamma H cut is actually the Gi mu n, where this mu n is also known as nuclear magnetron. So these are important for numerical problem that may come in the assignments or in the exam. So EH cut by 2 MP. Similar you have seen for Bohr magnetron, which is EH cut by 2 ME, mass of proton in this case, nuclear magnetron. In case of electron, it is Bohr magnetron, which is EH cut by 2 ME, and which value is actually 5 into 0.51 into 10 to the power minus 27 Joule Tesla inverse. And this Gi is actually a nuclear G factor, nuclear G factor. Now actually what is going to be the case, actually you can see if I replace the mu by gamma I, so I am going to get that our energy is actually, or you can say the Hamiltonian is actually minus gamma I and B. So where I is here is the vector. Okay. So now if you consider that that our magnetic field, whatever we are giving it externally, that is only along with the z axis, then it will only interact with the z axis of that moment, right? I. So it will be, so that then the energy is going to be minus gamma Iz B0, right? And what is Iz? That angular momentum is gamma. Iz is nothing but mh cross. You know, right? That angular momentum along the z axis is going to be mh. It is similar like the spin, spin for the electronic spin, similar, but the values are actually different. So now mh cut and b naught. Okay. Now this is whatever we got for. It is going to be the energy for each of the spin where it is interacting with the external field along the z axis. Now suppose we are now let me write it in along z axis, right? Then it will make sense. So now if there is alpha and beta spin, where alpha, for alpha m is plus half, right? And for beta m is minus half. then what is going to be the energy for alpha? So the energy is going to be actually negative, right? Negative gamma by 2 h cut b0. And what is going to be the energy of beta? That is plus, that is gamma by 2 h cut by b0. So what is the energy difference is going to be? Firstly, this has higher energy, right? This is positive, so actually this is actually going for beta and this is alpha. So this has energy at gamma by 2 h cross beta naught, and this is gamma by 2 h plus beta naught. This is minus. Now see one thing. So this energy total energy splitting is the energy gap will be gamma by 2 minus plus gamma by 2, it will be gamma h cut beta naught. So this energy difference is gamma h cut beta naught. So you can see if I increase the external magnetic field, that I can do, right? So if I can increase that, then the splitting will be more. So it is up to us, and this is what each 500 megahertz or 600 megahertz or 300 megahertz NMR. So you have learned that there is 300 megahertz resolution. So and 600, even 750 megahertz. NMR machines are there. So that means that we are so in each of the, so whatever is the magnetic field in 750, that is higher than that of the 600, and obviously then the 400 and 500 megahertz or NMR spectroscopy. So in that those cases that the splitting will be high, and that's why later you are going to understand that if the splitting is high, then you are going to get the first order spectra. So that we'll discuss it later. So but before that, so it is from the we can understand that if we apply an external magnetic field along the z axis, then the degenerate alpha and beta nucleus spin are going to have some difference in energy, and they will split according to the value of the whatever external magnetic field we are giving, and this is what the splitting in nucleus spin that does mean. Okay, now suppose different atoms have different splitting, that we know that for 13C the split we have something else, and so let us discuss about only one atom, that is right now it's proton NMR what we are going to discuss, right? So suppose we have some water. So NMR spectroscopy is we are going to use it for structure determination, right? So to get an idea about the structure, that suppose there is ethanol, or suppose some aromatic group is there, or so this is so we are going to use this NMR as a tool to understand the structure of a molecule. So if all the protons, if all the protons are going to resonate at the same, so suppose this is what the energy gap is between, right? So now we are going to give some radio frequency. Actually this gap is actually equivalent to the radio frequency. So now whatever we are going to give the radio frequency, it will resonate with that of the gap, and if it, so whatever will resonate with this gap, then that resonance peak will come, and we'll understand that okay, this is for the that particular signal is coming from that splitting. So after that, suppose all those protons, suppose in ethanol how many protons are there? So there are three different protons. Let me write it here. So suppose there are in ethanol CH3, CH2, OH. So there are three kinds of proton: one type, two type, and three type, right? So if all of them are going to resonate at the same frequency, then so you will get only one signal, right? Then how can we say that is from ethanol? And even if the same thing, then how can we differentiate between ethanol or suppose ether? So all, so that is actually the main thing, is that in NMR spectroscopy you are going to find that each of these protons are actually not equivalent, attached to different carbons. Actually these are not equivalent, and that is why we are going to get a different signal, because of their you can say the environment. What do I mean by the environment? I mean the uh, electronic environment. And suppose we are giving it a external field along the z axis. Now suppose this CH3 that have a different electronic environment than the CH2 and that of the OH. So those electrons are actually going to have some magnetic field that will oppose. So that will oppose the our whatever the magnetic field I am going we are giving from the externally, right? So actually that difference in shielding by that electronic environment is different for each of these different protons 1, 2 and 3. So that is what is going to lead to a different signals of proton NMR or different proton NMRs. So this CH3, CH2 or OH are not going to be at the same, not going to give the same one peak, but give will are going to give us three different proton peaks because of they have different electronic environment, and that is what determined by the shielding constant sigma. Shielding constant sigma. So now what I am saying that so each of them has different electronic environment. So each of them are going to have different shielding constant. So it is, so I am giving it B naught, but actually it is experiencing B effective, that is actually 1 minus sigma of B0. Understand what I'm trying to say? Now we already know the energy gap between alpha and beta spin of a proton NMR. We have found out that it is gamma H cut B naught. Actually, it is not going to be B naught, but effectively it is B effective, right? Which is 1 minus sigma gamma H cut B naught, right? And this is actually going to be equals to the H nu L, where nu L is the Larmor frequency or the precisional frequency. So this is what is being detected by the detector, and so in terms of we are going to get the nu L is Larmor frequency or the precision frequency about which the nucleus spin is rotating. So that is actually 1 minus sigma gamma B naught by 2 pi. So this typically comes at radio frequency. If so which energy is very less, very less. So now what I was trying to say, uh, okay. So this is one part. Now, so that is what is there. Now as you are experiencing, so here the sigma shielding is different for different uh, um, different another. So how we can define this shielding and other thing? So suppose you have known diamagnetic anisotropy, right? I think uh, you have learned this thing probably in benzene or aromatic rings. Suppose in case of benzene, what happens? So there are pi electrons are there, right? Suppose suppose here I am pointing, this means it is coming towards us. Suppose this is z axis. Okay, this is z along z coming towards us, and benzene is in the plane of that of the uh, screen. So it is coming towards us, and that is along the B0 is also working. Now in that plane, here there are pi electrons, right? So the pi electrons move like this, pi electron move like this, and the current will move like opposite to that, right? And if that is the case, then uh, you are going to, if the current is going like that, so you are going to see that the, there will be some inherent ring due to that in pi electron cloud movement of that pi electron cloud. You are going to see that you are having some magnetic field from inside. So here are protons, right? Here are protons. These are protons are there in benzene. You will see actually these protons are actually um, um, deshielded. So deshielded means it is experiencing uh, more magnetic field than the, if some, suppose there are porphyrin rings. I think you have porphyrin rings. I am not actually going to draw a proper justice of that. Suppose, I am just going to draw something like this. So in this kind of, where this is an aromatic system, I know I am not drawing it properly. So just get the idea that in this kind of system, suppose here are the system and there are also protons outside. Yeah, suppose in this kind of system, whatever there inside the ring is actually going to experience a shielding, means it will actually appear. Suppose this is the enema spectra, suppose this is the enema spectra, this is new. I am not going to the delta scale yet, so I will discuss about that. uh, So this is what in delta scale. And this is actually in radio frequency scale. Suppose what I am trying to say, these inner protons are going to be shielded one. So we can expect it is something somewhere around here which are shielded by the ring current, the magnetic field arising due to the ring current. So here actually inside that you can understand this is the magnetic field, right? This is magnetic field going inside, and that is actually opposing the external magnetic field. So that is what happening here, right? And in the outside, what is happening? It is, suppose it is going upward, right? It is going upward, and it is going on a circular thing, right? So means the whole area, it is not like I'm going for only one point. It is going like this, it is experienced by all the protons, right? So whatever the protons are outside the ring, that is going to experience this magnetic field plus whatever magnetic field I am giving externally. So suppose this, due to this B ring and B0, so this proton is going to experience B0 plus B ring actually, which is higher than, and uh, and in whatever there is the inside, so this is the outer ring, and inside those are going to experience B0 minus B ring, right? So they are shielded, these are shielded, and these are de-shielded. So in the shielded protons are going to be actually comes like in this region. For protons, actually you get it around 7, 8 for benzene or aromatic protons, and these are actually these are also aromatic protons, but in these cases these are actually going to be shielded, and we will get it at a lower value. Uh, so now when I was taking it, I forgot that one thing I have not mentioned yet, that is actually chemical shift. Actually, this is actually what a chemical shift coming from. So this uh, depending on this Lyman frequency, you understand that different protons will have different, means these protons, this proton and these, they are going to have different positional motion, and that is why they are going to have different Lyman frequency. Now you are, remember, I think Sarah said, suppose right now at our IIT Bombay, whatever new 12 Tesla or 300 magnetic field, external magnetic field, we are giving it. Suppose that
400 magnetic, we are going to use another 400 megahertz or 700 megahertz. Actually, you are going to get different, means this proton signal are different. Suppose in here if we use 300 megahertz NMR spectrum, so we'll get one at, suppose at 7. But suppose we are going to use 600 megahertz. If we go by the new scale or the energy scale, okay, so one for type 1 proton we are not going to get at 7, we are going to get at something different. But to be get a universal value of those signal or the proton, what we are going to take, we are going to measure it as a at a delta scale. That is actually your chemical shift in ppm values. So that will come at, actually we are, what we are going to measure at nu minus nu 0 by nu 0. Here nu 0 is the Larmor frequency for TMS. Nu 0 is the frequency of the standard or reference of the same uh, magnetic field what we are giving. So usually for a proton NMR, TMS is generally used, which is tetramethylsilane. Actually, it has, I think, CH3, 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 CH3. So all these 12 protons, I mean, there are 12 total number of 12 protons, and all of them have same electronic environment. So all of them are going to give a one signal, and as they are very much shielded, so, and this TMS actually is very volatile. They are inert. They will almost means mix with organic solvents. So that is why it is used as a reference in proton NMR. So actually the signal for the TMS actually is going to be at 0. What I'm coming. So actually, if you see, for TMS, suppose you are going to get some Larmor frequency, and for your proton you are going to some Larmor frequency, and then divide by nu 0 and 10 to the power 6 ppm. That is actually known as a chemical shift in ppm value or the delta scale. That is usually how we write. So if you do that, then you are going to get the same chemical shift value for the same type of proton. Suppose you are working on ethanol, CH3, CH2OH. Suppose you want to measure you want to know the signal of this type 1 proton, this is type 2, type 3. So this proton is going to be have the same signal at 300 or 600 or 500, even if you use a different magnetic field, whatever you use. Okay, so that's why you need a common scale, that is chemical shift in ppm values. Okay, so or the delta scale that is there. Another scale thing what I was wanted to discuss now, what you usually or one expect after this thing or after reading this thing. Suppose there are three kind of protons are there. Okay, there are three kinds of proton that we have established. Now what you expect in NMR signal? So the way I was saying or teaching, I was saying that there should be three NMR signals. So you expect that one signal for OH, one signal for the type 2, or one signal for type 3. So I'm not talking about where the delta is actually going, if this is 1, 2 and 3, actually delta is increasing this way, and for TMS you are actually going to get at 0, right? So for TMS, what is the thing you are going to get? Nu 0 minus nu 0 by nu 0, it is the 6, right? So that is actually 1. Now, um, actually, this is not the case. You are not going to get only one signal line. You already know that this is going to follow a rule, that is splitting rule, that is 2ni plus 1, right? I is the, where I here you take as nuclear spin, this I and that angular momentum is different. But what I am trying to say, how that has come, so that is coming from the coupling of between the electrons, coupling between the protons, right? That is coming from the coupling between the protons. So what do you expect for type 1 proton? You are expecting a triplet kind of thing. You are expecting for type 2, you are expecting a quadret, and actually for type 3, he is not going to couple with anyone because this is a labile proton and it is going to exchange with the solvent so fast that when it is it was there, it has some spin but it doesn't have any memory, because after the change, when it is coming, it doesn't have the memory that what spin it had. So actually it cancels out and there is no nucleus effective nucleus spin for that proton, and that is why it is actually not going to couple with any other proton. But you can have a broad spectrum of, you can get a broad spectrum of that, which, or even in case of some amines, NH amine group is there, so you are going to get those proton as a labile proton, and that is not going to affect in your coupling. So right now, what is the next thing we are going to discuss? That is discussed from lecture number 56. That is actually the coupling, and that coupling is actually coming from perturbation theory, and we are going to discuss that next. So first we will discuss the coupling between AX kind of system. You already know from the lectures that AX means these are two protons but have different electronic environment, and they are far separated. Okay, that is why the name is AX, not AB. Okay, so that, and they are not really far separated, but their chemical environment is different. That is here what is important. And suppose we are saying that that the we are assuming one thing, that the shielding constant for A is actually less than the shielding constant of the this kind of X kind of proton. Okay, and we are going to see that what is going to be what is going to happen. So we, for a typical case, we know that what is going to be the our so suppose we are saying there is no perturbation. Actually this coupling is going to be the perturbation, right? Coupling is going to be the perturbation. Now suppose there is no coupling. Okay, so no coupling. Then suppose for AX system, what can we guess? What will be the fast wave function? Can be alpha A, alpha X, right? It has the lowest energy because the spin of alpha, we have seen the spin of alpha is less here, right? Spin of alpha is going to be less than the beta, and if both have alpha, then it will have the lowest energy. Suppose this is our lowest energy, so this is the order we are going to be. This is the energy is lowest to highest. So what is going to be the psi 2 naught? What is going to be the psi 3 naught? We know that psi 4 naught is obviously both are having upward spin, that is or sorry, the downward spin beta A, beta X, right? And now what do you think? Alpha beta, which has lower energy? Alpha alpha A beta X or alpha X beta A? Alpha A beta X or alpha x beta a. That is why this approximation comes into the play, that we are going by the approximation or by that constant, that sigma, the shielding constant for a is actually less than sigma of x. Then proton a is experiencing uh, a is experiencing a larger magnetic field, right, than x. So the splitting will be more in a, right? So alpha a beta x will actually have the lower energy than alpha x beta a, right? So alpha a beta x is going to be a second wave function, energetically higher than the alpha a alpha x, and this is going to be alpha x beta a. That is what our wave functions looks like, right? Now we also know what is the Hamiltonian, zeroth order Hamiltonian, right? That we already discussed. That is our gamma. Then naturally, what is that actually? Gamma B naught. Now we are also considering the shielding constants, right? So that is what is coming here. Now for one purpose, this is 1 minus for A sigma A I Z A, right? Plus 1 minus sigma B I Z B, right? Now our E in 0 is actually going to be the psi n 0 H Hamiltonian psi n 0. This is when psi n 0 we are normalized, right? This is coming from a postulate for quantum mechanics, right? So the average energy, or if it was not normalized, then you have to take a denominator, that is psi n not uh, in bracket psi n not psi n not. So here all are the normalized. So this is going to be the energy. So let us calculate what is the what is the energy going to be for the first state E10. So that is going to be so gamma B naught. Let us take that thing outside the bracket. So it is sigma A. So I know what is alpha A alpha x. Then 1 minus sigma A I z. I am making one mistake, that it should have some, these are vectors, right, or the operators, you can say here, the operators, and 1 minus sigma b I z b here, and it is there alpha a alpha x, and it's closed. Now what is that? Gamma b naught, right? Now here we have to know this thing, that Iz operating on alpha is going to give us h cut by 2 alpha, that is the spin value, right? Iz going to be on beta is going to give us minus h cross by beta. This is nothing but the mh card, right? Angular z value of the angular momentum. Uh, so now, so alpha a alpha x, it will be like that. So 1 minus sigma a, shielding constant for a, and Iz operating on sigma a sigma x. So the Iza will only operate on sigma a alpha a. So we are going to get h cross by 2 alpha a alpha x, right?
and what else we are going to have 1 minus sigma b. Now this is going to operate only on the iz. Actually I have written it wrong. Izx, right? Izx, I have written all the things wrong. Okay, okay. Sigma x, now it is going to operate on this x, that is also alpha spin, so there is no problem. um, that is going to be also h cross by 2 alpha a alpha x, right? So what we are going to get is gamma beta naught h cross by 2 sigma x 1 minus a plus 1 minus sigma x. Actually, let me write it somewhere different. I will use the eraser. I'll take this whole thing outside the bracket because now it is all constant, right? That 1 minus sigma a, actually 2 minus sigma a minus sigma x, and alpha a alpha x alpha a alpha x. These are normalized wave functions, so it is going to give us 1, right? So this is what the energy is, and we can write it in terms of something like this: h cross 1 minus sigma a plus sigma x by 2, like this. So this is E1. So let me highlight it using a different color pen. Actually, I should have used blue color for all these lectures. Right? Maybe from next semester I will use this color. And highlighting I will use a different color. Okay. This is E1. So what do we expect for energy for the uh, psi energy for fourth state? So instead of alpha a alpha x, we are going to have beta a and beta x. So you can understand all of these going to be the same. Instead of is operating IZA on, it will going to operate on beta a, and IZX is going to operate on beta x, and actually it is going to give you, one time it will give you minus h cut by 2, and another time also it is going to be a minus h cut by 2. So the main difference is here you are going to get a positive h cut by 2, and there you are, for beta you are going to get a minus h cut by 2 actually. So you are going to get the same thing, but there will be a change in the positive value only. So actually in case of this gamma b0 h cut 1 minus sigma a plus sigma x by 2, this is what you are going to get for that. Let me also check if I am making it correct. Yes, that is correct. And again change the color. Okay. Now we are going to guess or calculate the value of energy for psi 2 and psi 3 naught. Okay. So energy of psi 2 naught is going to be alpha a beta x, right? Then outside there was minus gamma b naught, and inside there is 1 minus sigma a I a I z a or IAZ, however you want to write. 1 minus sigma x IZ of x, and there is alpha A beta x, right? Now here something is going to be a little bit tricky, that is 1 minus sigma A working on the same, so it is going to be alpha A, but h cut by 2 alpha A beta x, then 1 minus sigma x uh, minus h cut by 2, right here, um, alpha A beta x. So what is there in common? Let me see. Gamma b naught. So if you do this calculation by yourself, then the overall thing is going to be clear. That is what I am doing. That is why I am doing it here. Even though Sir has done this thing, Sir has not done this thing. Sir has done this thing quite elaborately, but not all the steps. So if you do that by yourself, then it will be very much clear to you how and why this coupling is happening. We generally, in interpretative NMR spectroscopy, we take this thing axiomatically that 2ni plus 1, these things, but the physical chemistry behind this is actually not known to many of us. So it is a better practice to know this thing. I hope you will agree. Now h cross by 2 I have taken out, and there remains 1 minus sigma A minus 1 plus sigma x actually, because there is minus sign is there, right? Then alpha A beta x, I'll close the bracket. Now it is going to be gamma b naught h cut by 2, 1 cancelled out, and it is sigma x by A. Sigma x minus sigma A, then obviously alpha A beta x is there. From the next steps I am going to ignore this thing, because anyway this is going to be 1, right, or 0 wherever is required. So it is gamma b naught h cut sigma x minus sigma A by 2, that is here E2. Now what is E3? That is minus gamma b naught alpha x beta A, then 1 minus sigma A iz A plus 1 minus sigma x iz of x alpha x beta A. Then the thing is that let us see, it will be more similar to the E2, not alpha x beta A, then iz will work on the beta A actually now, so it is going to give us minus h cross by 2, right, alpha x beta A plus 1 minus sigma x izx is going to work on alpha x, so it will give us h cross by 2, no negative sign, alpha x beta A. Here we are going to get, so now I am going to ignore that bracket function, what is going to be normalized, right? So I'll only write h cut by 2 common, 1 minus, I will take this thing first because this is positive, 1 minus sigma x, then it is going to be minus 1 plus sigma a, right? Because there is minus sign is there, and this is going to be anyway normalized, so I am not writing that bracket function. um, so this is gamma minus gamma b naught h cos by 2 sigma a minus sigma x, which I can write in terms of like this, right? uh, Gamma b naught h cross y is minus sigma a, minus thing I have taken inside, and this is going to be 2. So I will next write, I will next draw the energy levels what we got. Okay, I hope I am audible in the video. Let's hope so. Okay, so last time one problem happened. Let me check if that thing is happening or not. Last time one problem happened that this is was means attached to some Bluetooth device, and my audio was not coming. So half of the thing was actually not audible, or you can say was not there in the lecture. So okay, I have missed one highlighting thing. Yes. So now you can understand what is going to be the energies, right? So we already know. So we already know this is going to be the energy, right? This is the energy. This is for psi 4, that is beta A, beta X. Energy for this is beta A alpha X, third, then alpha A beta X, the second, alpha A alpha X is this. So this is the energy, how energy is going upward now, right? Now, uh, what are the, suppose there is, so it is during no perturbation or no coupling, no perturbation. Okay, now no perturbation, we are getting this case. So for this you can see that spin is from, so this is second, this is 1, this is 3, this is 4. So for a transition for 1 to 2, you can see that there is only spin change for x, right? If I go from there to there, only spin change for x. If I go for 1 to 3, then the spin change for a, right? If I go from 2 to 3, 2 to 3, the spin changes for both. Alpha A, for A it is going from, have I done some mistake? No, from 2 to, let us first consider 2 to 4, no, 2 to 3, let us see. 2 to 3, alpha A to beta A, means A alpha to beta. And X also is going from, have I done this correctly? Wait. Okay, so I had a doubt, so I went there and checked my notes, lecture notes, what given by the professor. I have found out that this is also, see here both the spin changes from 3 to 2 to 3, so it is also not going to be allowed by the, because of the one photon rule. But when we go from 1 to 2, there is change in the spin for x. When we go from 1 to 4, there is change for um, a. Now when we go from 2 to 4 there is change for, see, change for A, and when we go for uh, uh, go from 3 to 4, there is change in spin for X. So actually X and A, they are going to have different two different transitions, and when there is no perturbation, when AX is there, so you expect, so, you expect that for X you are going to expect 1, and for A you are going to expect 1, and the intensity is 2 is to 2, or you can say 1 is to 1, due to two transitions are happening, right? Now we are going to talk about the transition. Now when there is perturbation is there, coupling leads to perturbation, and that perturbation is, your perturbation is uh, H Jx, Jx the coupling constant, by H cut square, and something like the angular momentum of A and X. Now you all know the energy, perturbation energy, or the energy to the first order correction to the first order perturbation is actually psi 0 n your perturbation, or the Hamiltonian, and then your this wave function. Now what is going to be the first order correction to your first state correction? So that is going to be, so now that is going to be, um, let me write alpha A, alpha X, H J A X, H cut square, I A, I X. There is dot product between two these things, and there is, this is let me erase, um, alpha A, alpha X. Okay. Now, as you can see, this is a constant, so it will come outside. H J X by H cut square, and then alpha A, alpha X, and we can write this dot product in terms of a few things that you can see. I A, first X coordinate, X small x, a capital X small x. Please don't confuse it between, because I was very much confused when I have done the same. So suppose this is actually a dot product, so wait, I think we need to go to the main Google thing, stay in the call, and then we come back. Okay. Um, then alpha A, alpha X, similar, but here we are doing Y coordinate, right? This is a simple dot product, capital X, small y, alpha A, alpha X. So the treatment will be same for all, as you can understand. H J X, H cut square. Acha, I have missed one, so I'll write that. So alpha A, alpha X, I A Z. Previously I was writing it Z A Z X. Right now I am writing uh, something different way. Those are the same thing. Okay. Now we need to know these things also, this relationship. Alpha X, working on alpha will give you h cross by 2, but beta, which is not a eigenvalue operation. Similarly, you are going to get cross by alpha. Now when I y will work on alpha, you are going to get I h cross by 2 beta. And similarly I y will work on beta, it will go minus I h cut by 2 alpha. And when similarly you already know this, I z will work on alpha, you are going to get h cross by 2 alpha. I z work on beta, you are going to get minus h cross by 2 beta. So these are the relationship we are going to use it here. So in the first case, see alpha x and alpha x. Now ax will work on a and x is going to work on this. So what is the thing expecting? We are expecting h cross by 2 beta a for these two, and for these two we are expecting h cross by 2 alpha x, right? Then in the next case we are expecting alpha a alpha x. Now I y, first I h cut, I y will first work on alpha a, right? So that will give us I h cross by 2 beta, right? And I x y, when it will work on x, it will give us actually minus I h cut by 2 alpha. Okay, bracket close. Then what else do you have? Alpha a alpha x, this is easy. So this is going to alpha a z work on this will give us h cross by 2 alpha a. Actually I'm not writing those things, right? Alpha x beta x, here we are going to get beta a, and here we are going to get I have done some mistake, let me correct it. Ia y working on alpha a will give us beta a, and alpha x will give us beta x. Then this is alpha a, and again we are going to get alpha operating on alpha will give us Achha, so this is also operating on alpha, so this is actually plus, there is no minus there, so that was my mistake. And here is alpha x is going to return. Now you see alpha a and alpha x, and here we are getting beta a beta a alpha x, so those are orthogonal to each other, right? So actually we are going to get 0 from here, and here also beta a beta x we are going to 0 from here, but this is a normalization. See alpha a alpha x alpha a alpha x, so we are going to get only from this last factor we are going to get the thing h jx by h cut square into how much? H cut by a, h cut by a, that is h cut square by 4, and that is h jx by 4, right? And for similarly we are going to get the same thing from, actually I have written one thing in the first order correction. In the first order correction to the fourth is also going to be the same, just there for beta actually you see this iz, this is going to be both are minus, so minus minus it will come plus, so actually for this also you are going to get the same thing as e1. And also highlight this. Okay, so I will go to the next page, and where we will discuss the perturbation to the second, after the correction to the second state and third one. So this is, remember I hope alpha a beta x, right? And then so this part is there, h jx by h cut square is there. Now I will take directly that ix I x capital small. So there is going to be a dot product of all of this alpha a beta x, then plus alpha a beta x I a y I x y, right? Alpha a beta x. Then we are having another term, that is alpha a beta x I a z I x z, working on alpha a beta x, right? From here, see, similarly we will get some terms to be dissolved, that will not be there. As you can see, I x will working on beta alpha a is going to give me beta a, and then I x z I x x working on beta x is going to give me alpha a. So eventually it is going to give me 0, right? Then the next alpha a beta x. Then inside this a y, I y working on alpha a is also going to give me some eigenvalue, but not eigenvalue, some value, and then because that was not an eigenvalue equation, right? Because it is going to give me beta a, and from here I x y working on beta x is going to give me alpha x, right? So eventually that is not an eigenvalue thing, and I will get 0 from there. And what next? Here only for the z component I am going to get the similar things, and for here also IA working on alpha a I am going to get h cut by 2, I think h cut square by 4 I am going to get from the whole thing, but I guess here I am going to get it as a minus thing, because IAZ working on alpha a I am going to get h cut by 2 alpha a, but here I am going to get minus h cut by 2 beta x. So the h cut is plus and minus, it will going to give me like this, and eventually I am going to get that E21 is minus h, no, actually minus h jx by 4. And similarly for this also, see, similarly for this, here the thing is, I'll write once the main formula jx h cut square. Here the thing is for beta a alpha x, right? And here it is ix ixx beta a alpha x. Here I am going to get 0, right? Similarly, and then beta a alpha x I a y I x y, right? And then beta a alpha x is there. Here also for iy operating beta a, for this cases also I am going to get 0, right? Only the z term will get there, will remain there, which is beta a alpha x I a z I x z working on beta a alpha x. So I a z operating on beta a will give me beta a, but h cross by 2 here also I am going to get, as you understand, E3 first order correction to the third state, I am going to get as minus h jax by 4. So this is also going to be equal to E1 2, right? I'll highlight this here also, so it will culminate the whole thing. Let me use another color here. So firstly, when there is no coupling and when there was coupling. Okay. Okay. So this is the energy scale is going to be. This is the fourth one, beta A, beta X. This is beta A alpha X.
beta A alpha x. This is alpha A beta x. So this is all coming from that. Why this is higher than this? This is coming from the shielding that sigma A is less than sigma B, sigma x. And now we knew the energies, right? Energies for this. How much was that? Uh, that doesn't really. I will not that thing matter. So in the first case, see, there is addition of this thing means addition by h jx by 4 means there is destabilization here, here for the 1 4. How much destabilization was there? So that here is the thing. So the destabilization is same, that is h jx by 4 in both the cases. And in this case there was destabilization, there was stabilization, here there is destabilization, here there is stabilization by the same factor. The factor is ajx by 4 and here the factor is actually ajx by 4. Now see, previously your a to, for transition for either for a, or here the transition was from 1 to 2, it was for x, suppose. So what is the change in that? So for x you can see there are two changes. So there are two transition for x, right? One from here 1 to 2 and one other for 3 to 4. So for x you can see uh, there is change by see, the overall change is here it has destabilized, stabilized, and here destabilized by the same factor. So actually net change is addition of this, right? So there is h jx by 2 actually in energy terms, because h new is that, so h will be there, not there, but suppose this, so this was your x and this was your a, and this has higher energy splitting, right? That's why it is here, because sigma a is sigma x, that is there. So now actually you are going to get from x, for this case you see your energy gap is decreasing, so you are going to expect one thing from here, like in a gap of jx by 2. So here you expect this thing in a gap of jx by 2, and you are expecting another line here, the half intensity, because this is one and this is another intensity. Earlier it was falling in the same region, now it has difference. So jx by 2 overall, the gap between the two new signals coupled with jx, right? And for a also, see, with 1 to 3 and 2 to 4, right? For there now the change is that, see, a is destabilized by hjx by 4 and 3 is destabilized by hjx by 4, so you expect a line here, right? Less here, which is less than jx by 4, similarly 2. And for this case it is stabilized and it has destabilized, so here it has uh, by increased by jx by 2, right? 8 jx by 2, and in energy scale it is jx by 2. So that is why this is the coupling constant, that is jx, and here also it is jx. So in first order spectra you are going to see something like this due to coupling. Okay, that is why instead of two signals you are going to get two single for a and x. For x you are going to get a doublet, for a you are going to get a doublet. It's known as something like that. And Next, we are going to discuss if there is time. Yes, there is some time. I will quickly discuss for a. So this is for a AX system where A and X has different electronic environment and then some far apart. Now we are going to discuss a situation for A2 system. A2 system means A2 system means it is the protons are connected to the same carbon or the same atom, same nitrogen or the same oxygen, something. It is connected to the equivalent, or it is. I hope you are getting what I am trying to say. Now, for that case, the Hamiltonian will be little bit different from the. So when there is no perturbation, so the that is going to be little different because see in earlier case we got for AX system we got something like um, minus gamma beta naught 1 minus sigma a iz a plus 1 minus sigma x izx but here is both the protons are actually equivalent, so we will not able to distinguish, and so we'll write it something like that. So we're going to write it gamma beta naught 1 minus both is sigma a, right? There is no x, and so it is going to be sigma a1 plus I, actually I z1 I z2. So this is actually a1 a2. For simplification I am writing 1 iz, and for here actually the psi 1 0 is be the same, right? Alpha 1 alpha, now alpha a1 instead of I am writing it like that, alpha 1 alpha 2 2 3. Actually we don't know yet. After the energy we'll know, calculation of the energy, which is 3 which is 4, and this we know this is beta 1 beta 2. There are two possibilities, 1 by root 2 alpha 1 beta 1 minus alpha 2 beta 1, and another possibility is alpha 1 beta 1 plus alpha 2 beta, linear combination of them. Okay, because we can't really distinguish between the nuclear speeds. So now the energy for the first one is going to be alpha 1 alpha 2 minus gamma b naught 1 minus sigma a. This doesn't really matter right now, right? I z1 working on alpha 1 alpha 2, and then gamma b naught 1 minus alpha a I z2 working on alpha 1 alpha 2. So the first will give us z1 working on alpha 1 is going to give us the same. This thing I will take common, b naught 1 minus sigma a. Alpha 1 is going to give us h cut by 2 alpha 1, alpha 2 will remain same, and here also I am going to get the same thing, right? So actually uh, here I am going to get h cross by 2, here also I am going to get, so I multiply it by 2 because I am going to get something here also, here also. By sum I will h cross by 2 into 2, so actually I am going to get something, and alpha 1 alpha 2 are those are normalizable condition. I will get something there, alpha b naught h cross 1 minus sigma e4 naught. Let us see what we are going to get, beta 1 beta 2 minus gamma b 0 1 minus sigma a iz1 plus iz2 working on beta 1 beta 2. See, this is going to be the same as this, but iz1 working on beta 1 and beta 2 is going to give me minus h plus by 2, so I am going to get the same thing but in different value, right? H plus 1 minus sigma.
What about this thing 3 and 2? What 2 see what is going to happen? So it is quite big. 1 minus root 2 alpha 1 beta 1 minus alpha 2 beta 1. Then this thing is there. Acha, I'll do this thing in the next page. Okay, so I'll do this thing here. So I'll take this thing common, gamma b naught, gamma b naught 1 minus sigma a. Now 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Now here is iz1 plus iz2 working on 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, right? Now iz1 working on this will give us, so let me write it something like that. Now b01 minus sigma a is actually 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. iz1 working on this, okay? I am getting going to get 1 by root 2 alpha 1, so it will only work on alpha 1 not the beta 2, so I am going to get h plus by 2 alpha 1 beta 2. Now iz1 working on minus this thing, it will work on beta 1, right? So I am going to get h cross by 2 alpha 2 beta 1, because for beta 1 it is going to give me minus h cross by 2 and minus is already there, so plus minus minus plus. So this is what I got from here, and another what I am going to get. So yz working on this, so 1 by root 2 first iz2 working on beta 2, I am going to get minus h cut by 2 alpha 1 beta 2. Then iz2 working on alpha 2, again I have the minus sign, h cross by 2 alpha 2 beta 1, right? So actually you see what I am getting, sigma b0 1 minus sigma a 1 minus root 2 alpha 1 beta 2 minus alpha 2 beta 1 1 by root 2. Let me common with all these things, h cross by 2 alpha 1 beta 2 plus alpha 2 beta 1 minus alpha 1 beta 2 minus alpha 2 beta 1. You see all these things are alpha 2 beta 1, this thing is going to be 0. So actually you are going to get 0, but this is also an eigenfunction, right? So this also means is alpha 1 beta 2 minus alpha 2 beta 1. That is why the, so actually you don't require this eigenfunction for now, because we are doing that, checking that postulate from the quantum mechanics, and similarly you are going to get the same thing from the energy of the 3, right? Because there is alpha 1 beta 2 plus alpha 2 beta 1, so you are expecting the same thing. So how does that energy looks like? Let me draw that. In energy scale, it will actually look like this. For A2 system, energy is increasing, so actually this is your fourth, it is beta 1 beta 2. Then there are two non-degenerate states, that is 1 by root 2 alpha 1 beta 2 plus minus alpha 1 beta 2, right? Sorry, alpha 2 beta 1. And there is another state, it is alpha 1 alpha 2. Okay, so this is the energy. How does it looks like? So actually this is at almost zero energy, as you can see, right? Zero. And this is at minus gamma b naught h plus 1 minus sigma a, and I think this is at gamma b naught h cross 1 minus sigma a. So what are the possible transition here to here and here to here? Both of them have same energy, right? So that is why you are expecting a single line when there is no perturbation, right? This is no coupling is there. Now we are going to see what is going to happen when there is coupling, right? So let us see. So now part of A2 system, right? Coupling is there. Coupling is there or not, we will see. Okay. Uh, okay. So now also the same thing, that your perturbation is Hamiltonian is H J, now JA by H cut square. Now this is IA1, I1, something I1 into I2, that is right, something like that, right? And your first order correction to the energy is going to be, or it is going to be same, right? Psi 0 n H1 psi 0 n, like this. Now let us see what is the first order correction to the psi 1, right, for A2. So E1 1 is, I1 is alpha 1 alpha 2, right? Now H J, we can take this thing outside, that is correct, and again this means 1x I1y, right? A1x 2x alpha 1 alpha 2, then plus alpha 1 alpha 2 I1y I1 2y alpha 1 alpha 2, right? Then we have alpha 1 alpha 2, then we have I1 z I2 z, right? Then we have alpha 1 alpha 2, something like this. Now we all know the relationship x will I1 x will operate on this, not, and this will operate on this. Let us see what we are getting at. So E11 we are going to get something like, so H JA by H square is already there. Now alpha 1 alpha 2 I1x operating on alpha 1 give us beta 1, and next one will give us beta 2, and in total will give us this, right? Then we'll get alpha 1 alpha 2, we'll get IH by 2 h plus by 2 whole square beta 1 beta 2. See, so this is going to give me 0, right? Alpha 1 beta 1 alpha 2 beta 2. Then for the z component we are going to get alpha 2 alpha 1. Here we are going to get h cut square by 4 alpha 1 alpha 2. So we are going to get something from here only. Similar like the AX system, right? We are going to get something like this, because h cut square cut. So we can expect the same thing from the beta 1 beta 2, right?
There it was minus h cross by 2. These two I1x, I2x, I1y, I2y, this term will get cut out, but the z component will give you, for beta 1, beta 2, it will give you minus h cross by 2, 2 into minus h cross by 2. Eventually minus minus cut out, and you are going to get this h crosses by 4, and then multiplied by hja by h vector square, it will give you hjaa by 4. So this is what you are going to get. And next, let us see what you will get as the second or first order correction to the second thing. So this is actually going to be quite broad. JAA. Let me do it in the next page. Even though there is some space in this page, I will not do here. I will do this thing here. V1, 2 is actually, that thing is there outside, which is A by 2. Sorry, h cut square. Have I made this mistake earlier also? Then 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, right? Alpha 2 beta 1, alpha 2 beta 1. Then we have that perturbation I1 2, I1x, I2x. Here what we are doing, that I1 into I2 is I1x into I2x, right? All the other cross terms will cut, that cross product. I1y, I2y, I3z, I1z, I1, I2z. Now we do the same thing here. 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then this is actually not the close, but this is one of the bracket, right? Then we'll have 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, right? Will have I1y, I2y, 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then we'll have 1 by root 2 alpha 1 uh, beta 2 minus alpha 2 beta 1, I1z, I2z, 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Now hjaa by h cut square will be there. Now let us see what we are going to get for first term. Alpha 1 beta 2 minus alpha 2 beta 1. Now I1x is going to work on, I1x is going to work on both of these. Let us see what we are going to get. So I1, both of these means both these terms, this and this, this and this, but only on each part. So I1x, but we have to do this together, right? I1x will work on this, I2x will work on this. So I1x will work on, so we are going to get beta 1, right? With the value of h cross by 4, because 2x is also there, which will work on this beta, and this is going to give us
beta alpha 2 is going to give us alpha 2. Now the next is uh, minus is there already, so I am putting that minus there. Then I1x working on beta 1, so that is going to give us h cut by 2. Beta 1 is going to be alpha 1, and alpha 2 is going to be beta 2, and it is going to be the square, right? Here there is no change in the thing, and here what you are going to get eventually is actually, I'll write it here, outside the thing you are going to get minus h square by 4. If you take that thing common, we are writing 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. And then beta 1 alpha 2 you are taking common, my not common means you are taking this outside, minus h square by 2. So here there is a alpha 1 beta 2, 1 by root 2 is there. I'm not taking that out, and beta 1 alpha 2. So see, you may have doubt that why 1 by, so this is actually going to be a normalized condition, not 1 if I take 1 by root 2 outside, 1 by root 2 into 1 by root 2, that is half outside, then it is not 1, because this is the overall your wave function 1, that 1 by root 2 into this, then that's why it is coming here. And then see what is going to be the next part. The next part is also 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then I1y will work on like that. Okay, I1y will work on I1y will work on alpha 1. So that is going to give us IH cross by 2 beta 1. Now I2y on beta 2 is going to give us minus IH cross by 2 alpha 2, right? Then next we are going to get I1y working on beta 1. So that is again going to give us minus IH cross by 2 alpha 1, and I2y working on alpha 2 is going to give us IH cross by 2 beta 2. Okay, so see from here what we are going to get. So we'll take common. So this is, we are going to take common I h square by 4, and minus is also there. So eventually this is h cut square by 4 minus h cut square by 4, and the rest of the thing is again 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, and 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, and this is 1, this is 1. So you are going again getting minus h cross by 4. And for the last part I will show you from here. See, Iz will work on alpha 1. So no, let me write it here. So 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1, then 1 by root 2 take Iz1 will, this is alpha 1 beta 2, right? But it is going to give me h cut square by 4, because for the first one you are going to get h cut by 2, and the second one you are going to get minus h cut by 2. So overall you are going to get minus h cut square by 4, right? And for the next you are going to get the same thing, but here it is plus h cut square by 4, because the minus sign 9 was already there. So here what you are actually getting is 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1 common. Here also you are taking minus h cut square by 4 common. Then you are going to get 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Then it is 1, and you are also getting minus h cut square by 4. So actually what you are getting, I am making it simpler here, h jax ja by h cut square into 3h cut square by 4, and you are getting 3, actually minus, so minus 3h jaa by h cut square, sorry, h cut, h cut. So this is the first order correction to your, sorry, first order correction to the second one. Now I'll give you the third one. So E, first order correction of the third one is aj by h cut square 1 by 1 by root 2 alpha 1 beta 1 beta 2 plus alpha 1 alpha 2 beta 1. Now here is the plus sign. You may think it is going to give us the same thing, but actually it is not going to give us the same thing. That is why I am doing 1 by root 2 alpha 1 beta 1 plus alpha 2 beta 1, right? This is the first bracket. Then we will have 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1, then I1 y I2 y, then 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. Then we have 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1 I1z I2z, 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. Okay, so this is what is we are going to get. So you should practice these things by yourself, or you won't be able to understand what is actually happening. You are aware, but you will forget. Eventually, I will also forget, but this is a better practice to do at least once. So when you revisit, it will be easier. 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. So 1 by root 2, taking common I1x1, that is square by 4 beta 1 alpha 2, that is what we are going to get for the first, and then for the second we are going to get um, second also we are going to get alpha 2, we are going to get beta 2, and for alpha beta 1 we are going to get alpha 1 alpha 1 beta 2 beta 1 alpha 2, and both of them we are going to get the same thing, right? What happened in the previous case is a minus sign was there, right? That's why the problem was there. No problem, but the confusion. Now plus 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. Now what we are expecting, alpha 1 beta 2 will become beta 1 alpha 2, right? Beta 1 alpha 2, but in exchange what we are going to 1 working on this, so I h by 2, and for this beta, so square of this beta minus 1, right? And here we are going to get the same thing, that minus plus minus I h cut by 2 square of this, then alpha 1 beta 2, right? Alpha 2 will become beta 2 and beta 1 become alpha 1, and for one case you will get minus I h cut by 2 and another case you will get I h cut by 2, so eventually this will be solved. And here you are going to get 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1 1 by root 2. Here alpha 1 beta 2 will be there. Here the thing is that you are going to get a minus sign, I guess. Minus cut by 4, and here also you are going to get h cut square by 4 beta 2 alpha 1. So from the first one you are going to get h, the first one. So this, if I take common h cos by 4, you see that there will be some normalization thing and it will become 1. Then alpha 1 beta 2 alpha 1 beta 2, here also you are getting alpha 1 beta 2 plus alpha 2 beta 1, and here you are getting minus 1 into I h cos by 2 square of that, and here you are getting h minus h cos by 4 as common, right? So this and this will get cut, and h j by h cut square actually into, and here this thing is also there, so this is going to be minus 1 into I h cut also going to be minus h cut crosses by 4, right? So minus minus cut, so actually it is going to give you the same thing, hjaa by 4. So what again we are seeing here, that so no coupling, this by 2 and coupling, right? So there was degeneracy here, beta 1 beta 2 alpha 1 alpha 2, here there was 1 by root 2 alpha 1 beta 2 plus minus alpha 2 beta 1, and what has happened is these two cases again go up to this by h by 4, these also go up by same factor, that h destabilize. One of this, which is the plus one, that has gone up here again, HJAA by 4, but one of them actually gone down, that is by, actually this was 0, right? So this has gone down, so the scale is not perfect, here gone down by, stabilized by 3 HJAA by 4. Okay, so now what you can see here, your energy was, two transition was there when there is no coupling, both of them has the energy as uh, gamma b naught 1 minus sigma a, both the cases. Now see here actually two things coming, one is one photon rule and another is delta A should be 0. Because why this spin multiplicity is coming? Because now it is on the same equivalent, so you have to consider the spin also. So see, for alpha 1 alpha 2 it is the symmetric, is for the plus is symmetric, beta 1 beta 2 is also symmetric special function. So all of these will are going to have a singlet spin state, singlet, and only one. Sorry, these are all symmetric uh, spin state. That is why these are all triplets. Okay, all triplets. They have anti-symmetric special part, and only one of them, the second one, is actually going to be the singlet one. Right? Okay, this is the spin state. Now delta is equal to 0, so there will be so again one photon rule is there, so you can't have from 1 to 2 you can't have, and 2 to 3 you can't have, right? You can't change two spin by one photon, right? Now, when this delta is equals to 0, that restriction is also coming, so you are going to only have the so you could have. So let me draw a nice picture of the patterned one. So that is the fourth one, patterned by A by 4. The third one, patterned by J by 4. The second one was here only, but it was stabilized by 3J by 4. And the first one was here, it was patterned by. This is actually the correct pattern. No coupling. Here it is patterned by A by 4. So see, so earlier two transition was possible. This. Now what are the transition possible with one photon rule? Same, 1 to 2, 2 to 1, 2, 2 to 3, and 2 to 4, and 3 to 4. Right? Is this making sense what I am saying? Now see, when the this related to delta is equal to 0 is coming, now whatever related to the 0 is not actually will be there. So you are going to see only a 1 to 3. 1 to 3 was also there. Right? You are going to see only this. This is cut from 2 to 4. It is cut, right? So only this one, and 3 to 4. So this will also. So again you are going to have the same thing. And what about the energy? See, here it is in 2 for 3 to 4, both are destabilized by the same energy. So there will be no change in the splitting, effective splitting, effective change. There is some change, perturbation was same. Both are destabilized by 8J by 4. So you can't see that in the spectrum. And in case of 1 to 3, the same, both are destabilized by 8J by 4. So you can't see that thing in the spectrum. So there is coupling in A2 systems, but we cannot see them. Let's see that in the spectrum. Okay. So with that, we can also go to AX2 system or AX3 system, where actually what happens, that suppose X will get splitted by A twice. Okay. So this is for X.
Now A, so so suppose this was x because we are taking sigma A less than sigma x, right? So if this is the energy here in this case nu, so nu is there. So for A, first it was 1, okay. Then by the first x it is split by 2. Then these two again will split into 1 is to 2 is to 1. So eventually you are going to get 3 for A, right? For this system 1, 2, 1, and this is 1, 1. Okay, and the gap between each will be again Ax, because first it was 1, then it split it into 2. The total gap was Ajx by 2. Again it is split into the same, right? Now for this also let me draw Ax3, what one should expect. Suppose X3 system, first X is split into 2, okay? This is Jx by Jx for X. Now for A, first there was 1. Now by the first, suppose by the first X, it is going to be half of this, right? So it is going to be the Jx again, huh? For A. Now, now the second, the first X couple split it into 2. Now the second will again couple this thing into 2. Here 1, here 1, 1 for this and this will 2. So 1 is to 2 is to 1. Now the 3 will come. Now the third, actually the third uh, x is going to split here, here. Now this has 2, right? So for this it will have another 2 here and 2 here, right? For this, and now this have 1 here and 1 here. So eventually this will be 1 is to 3 is to 3 is to 1. So this is how it is going to be. And the gap between each of them is going to be Jx, Jx, and Jx. Okay. So this kind of question for AX3, so you know already 2ni plus 1 formula, but this is how this is coming. One more important thing, see, this is coupling taking place in for a particular proton, right? Coupled by this. So, but the value between these is actually much higher than this coupling constant. Okay, that is why if you change the magnetic field, this A and X, this gap will increase, but the Jx is not going to be increased. Okay, so that is what you also kind of remember. So when the gap between these two are very less, suppose A and X, and you have a much high coupling, uh, which is actually uh, means complicated to see, then you should use higher magnetic field so that AX and have different much more spacing between them, and you will see a better fast order spectrum. So for today, let us stop it here, and we will come back to this. Will come will for the next will maybe next week we'll discuss the last week and uh, problems, and we'll have another week to discuss um, some other things, maybe uh, some other numerical problems, maybe we'll discuss that, and then that is how we are going to finish that. Okay, I hope you were
listening this thing or seeing this thing in the YouTube. I hope this will help you understanding the thing that is taught already by the Professor Datta. And okay, with that, today let us finish this. We'll meet you next week. Thank you. Thank you for listening.